Good afternoon, everyone. Thank you for joining me for this vendor demo. My name is David McKittrick. I am Outreach and Training Manager at a company called Blue Marble Geographics. We are headquartered in the state of Maine. I'm actually hearing my own audio in my ear, so I'm trying to figure out how to prevent that happening. Let me just, I believe that should work. Hopefully you're still hearing me. I've just turned my own volume down, so that's a little bit easier on my own ears. Okay, so where was I? Yes, my name is David McKittrick. I'm Outreach and Training Manager for a company called Blue Marble Geographics. We are headquartered in the state of Maine, a little bit further north, up on the East Coast. I should say a former resident of North Carolina. I did live in Asheville for 9 years. Beautiful part of the world. So I'm glad to be home again in a virtual sense. Over the next 30 minutes or so, a little less than 30 minutes, I'm going to be talking a little bit about Global Mapper. That's our primary application that we develop. We're a software development company. Global Mapper is a desktop GIS application. I'm going to talk a little bit about the software by way of introduction, but specifically what I'm going to do is give a demonstration of a very specific tool within the application. As you can see, my presentation title is Got a Drone, Now What? Mapping with your drone data in Global Mapper. We're going to go through a simulation of creating some 3D data within the application. We're going to use a process called Structure from Motion, and we're going to essentially recreate the three-dimensional environment within a geospatial or mapping context. So if you have a drone, it might be something you're interested in doing yourself, collecting imagery on a drone. This is certainly a workflow that you can follow. I do encourage you to ask questions of me. I know that there is a chat function on the right side of your screen. Feel free to use that. I'm going to take or answer those questions at the end, but feel free to type them in whenever you want. If you want to continue this conversation offline, maybe a longer conversation, I will also give some contact information on my final slide before I wrap up at the top of the hour. So again, feel free to ask those questions in real time. I'll try to answer those at the end or by way of follow-up. So what is my objective today? What am I hoping to achieve? Well, I'm going to use Global Mapper, and I'm going to transform overlapping drone collected images into, as I mentioned before, a three-dimensional geospatial model of our target area. And I'll say that the target area that I'm going to be working with is an area in Vermont. Now, we have some sample data in kind of rural Vermont. We're going to take some data, some images captured for that area, and I'm going to go through the process of generating our 3D data. Specifically, it's going to be a point cloud. With that point cloud generated, we're also going to do some point cloud processing. We're going to generate a surface, and hopefully, time permitting, we'll keep an eye on the clock, maybe even generating some contours or going through some more analytical workflows with that data, reminding you at the end that this all began with simple drone collected images. We will be basing this on the principles, as noted here, though, of structure from motion. And by way of introduction, those of you who are not familiar with that, I'll describe a little bit about what we're talking about here. So let me begin again. Well, I kind of jumped ahead a little bit, looking at my agenda as noted before. We're going to answer the question, first of all, what exactly is Global Mapper? There may be, I'm sure there are folks in attendance who are not familiar with our application. We'll start with a high-level quick overview of what exactly it is. We will then talk a little bit about the technology, the underlying technology that we'll be using in this workflow. Structure from motion, what are we talking about? We will then see it in action. That's where I'm going to get out a PowerPoint and actually show the application running or show that process running in our software. And we'll, time permitting, again, I'll keep an eye on the clock, but we'll go through some analytical procedures based on what we generate through that process. Maybe initially identifying the points that we generate, which are likely to be ground points. The structure from motion will generate a 3D representation of everything it sees within the images, and we maybe want to remove those points that are not ground. Identification of ground points, maybe creating a DTM from that, a digital terrain model, and ultimately generating some contours. So that is my plan, again, for the 30 minutes or so that I have available today. So what exactly is Global Mapper? If you have never looked at it before, it's worthwhile even going to our website and maybe downloading a trial. It's desktop GIS software. Began its life, boy, almost 25 years ago now, as a project for the USGS. It was developed initially as a data viewer. The application has taken on a life of its own in the intervening 25 years, and it's now a very robust, very powerful GIS application. Some of the defining characteristics that make this unique, well, number one is the number of data formats it supports. At last count, we're over 300. So regardless of what data you're working with, Global Mapper can be used to both import and, in most cases, export that data as well. So a lot of folks are using this just simply as a stepping stone between maybe one application and another. It does include a complete suite of vector and raster processing tools. It offers extensive analytical tools, particular strength as noted here in 3D analysis. A lot of the development work we've done over the last number of years have focused on the display rendering analysis of 3D data, and certainly want to see examples of that today. A lot of the work we do in the GIS space is now 3D, inherently 3D. So Global Mapper has been developed to kind of address that increasing use of 3D data as opposed to kind of the traditional top-down analysis. The application includes an optional LiDAR module. LiDAR, point cloud data may be derived from the laser scan system, or it may be derived from some other process. And we'll see an example of that today, where we're going to generate a point cloud that's not LiDAR derived, but can use a lot of the same tools in the application. But the optional LiDAR module in the software provides a lot of processing tools for point clouds, things like ground point identification, feature extraction from buildings, vegetation, et cetera, et cetera. So if you're working with point cloud data, and I assume by virtue of the fact that you're attending this presentation, you're interested in this kind of discipline, you may want to be taking a look at that LiDAR module as well as an add-on for the base product. So again, just quick overview of Global Mapper for those who are not familiar with it. So the other what is question is, what is structure from motion? What is the underlying technology that we're going to be using today? Well, as noted here in this little crude screenshot on the left side of my screen, you can see a simulation of some captured images. We are going to take simple top-down drone collected images and ask Global Mapper to analyze them. This is an image analysis process that's going to be used to reconstruct or construct a three-dimensional environment. And it does that by comparing the literal pixel patterns within each image. Now, assuming that we have some sufficient texture, in other words, within each image, there's enough distinguishable features, Global Mapper should be able to identify those patterns in multiple images. So in order for this to work, we need to have overlap. Similar to the way your eyes work, and you're not seeing what I'm doing with my hands. Covering one of my eyes, I can obviously lose that depth perspective. With both eyes, I can see these objects in the distance from a slightly offset perspective, which gives me the ability to see depth. Take that principle and apply it from multiple perspectives, and you can discern the three-dimensional characteristics of an area. And that is inherently what we're going to be doing, looking at features from multiple perspectives as a means then to reconstruct that as a three-dimensional model. So bottom line here is, if this is something you're interested in doing yourself and you're out collecting images, you may want to be making sure that you have that degree of overlap to ensure that process is actually going to work. Again, recurring patterns of pixels are identified. What do we see? Do we see a particular structure? Do we see something on the ground? Maybe even vegetation patterns. If we see those from multiple perspectives, from multiple vantage points, if you like, we can run through the process of identifying where they are in three-dimensional space by performing a simple triangulation, basically, identifying where they are based on the triangulation process. Now, this is a little bit, again, of the kind of underlying technology. As you will see, the implementation of this in Global Mapper is very simple. Your raw material are your drone images. The output products, as you will see, are three-dimensional data sets. And last bullet here notes that if you want to increase the accuracy and precision of what you're generating, ground control is important. Now, ground control in this context works by surveying identifiable features in your target area, whether that be existing features or something you place on the ground prior to collecting the images themselves. Knowing the precise three-dimensional coordinates of those control points, and identifying those control points in the corresponding images that are collected will improve the accuracy of what we generate. It's not required from a technical point of view, but certainly recommended from an accuracy point of view that you do incorporate ground control into this workflow. And I'll show you in my simulation where we would do that. So at this stage, let's take a look at structure from motion in action. Now, I'm going to quickly go through, as I mentioned, a simulated workflow. And for this, I'm actually going to bring up an instance of Global Mapper. I have on the screen here already loaded a low resolution image just to give us a little bit of a visual and geographic perspective. This is a little farm building somewhere in rural Vermont. Now, don't worry about the quality of this image. This is not our final product. This just shows us our target area. The source data for the process we're about to embark on are drone images, and Global Mapper allows you to simply load those into the software as what we call picture points. Because each of the images is tagged with its coordinates, the X, Y, and Z coordinates, it will actually place an icon in three-dimensional space denoting where each image was taken from. So if I turn on that layer, you'll see the individual icons. So all I've done at this stage is simply dragged and dropped literally, looks like a couple of hundred images, maybe 150 images onto the screen. You'll notice the visual indication as to the direction of flight and obviously the location of each image. If I click on one of these with an info tool, there's a couple of things I can display. One is the information about each image, and just having selected one randomly, we see all the metadata for that specific photograph. We can do some initial checking. We also see the approximate footprint of that image. If I choose another one, you can see those footprint models, and you can see in this case, I do have a significant amount of overlap, so I'm confident that this process will work for what my intention is. Also, we have the option simply to display the image itself, and this will trigger the display in whatever your default image viewer is. In my case, it's an external application called Irfan View. It just popped up a thumbnail or a preview of the image, and again, I can quickly scan around and take a look at the images by referencing them in their geographic context. So this is my raw material. This is the data that I'm going to process. The tool I'm going to use is what's referred to in Global Mapper as pixels to points. Scenario here being we start with images and we generate a point cloud. So pixels to points is a button right here in the toolbar. If I select that, it brings up the dialog box that allows me to set up the parameters for this process. Well, obviously you can see everything's blank right now. So the first thing I need to do is load the images that I had preloaded onto my map screen. And the way I do that is simply File, and I can load the picture points. I can also load points, the images from an external file, but I'm going to load those that were already added as picture points. So from the file menu, sorry, my cursor's moving a little bit here, we'll go ahead and add loaded picture points. Now, this will take a little bit of time, but you'll see eventually a tabular view of all of the individual images, and you can see certain components of the metadata are also displayed here. Now, the critical parts of this are the fact that each image knows where it belongs in three-dimensional space. These are the coordinates and the relative altitude of the drone when each image was captured. And as I scroll through each of these, you'll see the preview window on the right side refreshing and giving me, again, a quick view of each of these images in turn. I'm looking at an area that's pretty rural here. Obviously, a lot of trees, a lot of, there we go. We've got some buildings coming into view now. Now, noting what happens with the adjacent images, I'm looking specifically at this farm building. Hopefully, you're seeing this on my screen, right over here on the left side. As I transition through each subsequent image, you will notice that my perspective of that building changes slightly. I'm looking at it again from a slightly offset vantage point. Now I'm starting to see the wall on the far side of my building, which I wasn't seeing before. And this again illustrates the inherent process we're going to be applying here, where we're looking at a set of pixels basically in that image from multiple perspectives. If I went to the adjacent flight line, I would see the same images. I would see the same building. Slightly different perspective here. We're obviously flying back along an adjacent path. So we're seeing the same building from a different vantage point. So when we initiate this process, it will be an analysis of these images that will allow the application to recreate this again in a three-dimensional context. Now, a few other settings that are relevant, ground control points, which I don't have in this case, but if I did, they could be loaded here. They could be loaded from an external text file, perhaps, that I collected, or even from a file that I already loaded into the application, maybe a shapefile containing vector points where my control points are. If there were control points, let's assume that we have a control point at the corner of this, maybe this green, or maybe we have laid out a target, for instance. I would identify that by simply clicking on the map view or the image view and tagging the control point, the appropriate control point. You basically just determine where the coordinates are for that location in three-dimensional space, and repeat that for each of the control points and for each of the images that contain a view of that control point. Again, that addition of the control points is going to improve the accuracy of the output that you'll be generating. There are a number of other settings in here. I'm not going to go into the details in the interest of time, but you can reduce the image size to improve the speed, use a relative altitude. If you do not know the inherent elevations based on control points, you can at least establish a starting altitude, and all of the Z values for the output point cloud will be derived from that basis. So a few other options here, as I mentioned. The output is going to be threefold, depending on what you need, but you are, as part of this process, going to generate a point cloud, similar to LiDAR, but not LiDAR. You'll generate also an ortho image. Now, an ortho image is an image in which, in theory, every pixel is in the correct location in three-dimensional space. All of the inherent distortion from the original has been removed, and it is geographically positioned correctly. Now, the ortho image that's generated in this workflow is actually a derivative product of the point cloud. It's a gridded version of the point cloud that's used to generate the ortho image, and we'll see that in just a second. Also, and this is the eye candy, we generate what's called a mesh, or a three-dimensional model based on the point cloud. One of the output components of the point cloud, because it's based on these images, are going to be the corresponding colors. So we will generate a three-dimensional model of this area with the colors assigned, colors from the original images assigned as textures on this mesh. We'll see that in just a second as well. Now, if this was the real world and I had established the necessary parameters here, maybe established ground control, etc., I would click the run button at this stage and I would let it go through its process. Probably about an hour and a half with this imagery, with this number of images and this level of resolution before I get my results. It is a time-consuming process, but it doesn't require any specific hardware. It can be, I'm running on my laptop right now, my simple Dell laptop, and yes, it took me a while to generate the data, but it works. Now, I'm going to pretend that I've done that. Obviously, we don't have an hour to sit around and wait, so I'm going to close the dialog box, and I will show you the end result of the process. So this is a little bit like a cooking show. I'm going to show you one that I prepared earlier. I'm going to turn off the original images. I'll also turn off this low resolution top-down view that I had displayed, and I'll turn on the three output file formats that we've generated. The first is my point cloud. This point cloud, if I expand a little bit here, has 15 million points generated from analysis of those images. I can pop this up in a 3D view, and we'll start to see some of the three-dimensional characteristics that have been identified through this analysis process, through this structure from motion process. Now, I'll be looking at this 3D view again in a few minutes, but as an initial preview of my point cloud, you can see that quite clearly here. Also, as noted, we generated what's called an ortho image. Now, this ortho image is simply a top-down view. You'll notice there's a few gaps here, and that's because of the way the imagery was processed, but we have a high-resolution top-down view of our target area as a simple raster layer. And you can see, I'm going to zoom in a little closer here, and you can see a little more clearly. So that is another output product from this process. The final output, as I mentioned before, is a mesh. And the mesh initially will look like the image, except this is a three-dimensional file. It may not look like it, but this is actually a vector file. And if again I pop up my 3D view, you'll see the three-dimensional characteristics of our target area in all its glory. I'm not sure if this is coming through in a kind of a smooth way in my streamed version, but you can see what I was able to create from simple top-down overlapping images. I was able to create this three-dimensional structure of my target area. I find it interesting that the building walls came through as cleanly as they did, because the images that we previewed were top-down, they weren't oblique. This tool can also be used for oblique images. So maybe you want to fly a pattern around a building if you really want to get better quality for the sides of your building, for the walls of your building. But even without, just looking at this top down, it did generate some very high quality data. Also note over here, we have a few vehicles parked in the field here. This is actually the drone operators' cars. If we look at some of the early images, we actually can see those, and they appear in the output model as well. So this is again, a mesh or three-dimensional model derived from the point cloud, which was derived from the overlapping drone images. Now, I've got about 5 minutes left here, and I want to put this in a little more of an appropriate context. Generating these three-dimensional data sets is really cool. Lots of eye candies, lots of oohs and ahs. It really looks good. But to give this value, I'm going to go through a more meaningful workflow. And for this, I'm going to go back to the point cloud itself. Now, the point cloud is noted here. I didn't zoom in very clear, but it is points. We have points displayed here. However, these points are not intelligent enough to know what actually they represent. I've visualized the point cloud now based on classification. And as you can see, they're all gray. We don't have any local intelligence. They are effectively unclassified. In order to make this meaningful, what I want to do is identify the points in this point cloud that are ground points. And there's a built-in algorithm in Global Mapper for doing that, for analyzing the geometric structure and determining which of these points are likely to be ground. Before I embark on that process, I first want to perform a thinning operation, because there's way more points here than I need. In fact, if I look at the metadata for this generated point cloud, I can see there are about 360 points per square meter, way more than I need to generate a decent DTM. So what I'm going to do is initiate a thinning process to remove a little bit of the redundancy here. I'm going to thin this down by a factor of 5. And one of the options I have here is to retain full resolution for 3D features. In other words, if I have objects that are inclined or even vertical, I will retain full resolution for those. There's an interpolation process applied, but for horizontal areas, I will apply my output resolution of about 5 times the current point spacing, and we'll click OK. Now, this technically generates a new layer, so I can turn off the original. And hopefully you saw when I turned it off, we have a few less points. Once again, we can go into the metadata and see the results of that. Now we have about 50 points per square meter. Yes, you could still say it's way more than we need for our DTM, but that's okay. The next thing I want to do, as I mentioned before, is identify ground points. The ground identification is an automated process. I'm not going to pause here to go over the individual settings, but we can define some of these characteristics here in terms of what it recognizes as ground and what should be ignored. Based on the settings I had previously applied, I'm just going to click OK. And as a result, you should see brown points assigned where there are ground points. Gray points are still recognized as non-ground or technically still unclassified. Now, this gives me the basis to generate a DTM, because I can ignore the points that are not ground points, and I can perform that filter just very simply by filtering the points that are now displayed. I'll turn off all of my points, or rather I'll turn off the unclassified or never classified points and retain just my ground points. We'll click apply just to verify that that worked, and you can see now all I have on my screen are ground points. Final step in this workflow, I'm going to simply create a DTM, generating an elevation grid based on the currently active point layer, the one that's thinned, noted here at the bottom of the list. I'll click OK. Again, there are settings I can apply to determine the output characteristics. I'm not going to spend the time to go through the details. We'll simply click OK, and we should see, when this process completes, a raster surface model from which I can create contours or conduct any type of three-dimensional analysis. And I've left some holes in here just based on my settings. I probably should have tightened it up a little or tightened up the interpolation, but you can see there's a few holes. But this is now a three-dimensional raster surface model, a DEM, if you want to describe it that. Specifically in this case, it's a DTM. We can adjust some of the visual characteristics, maybe the shader. I'll just choose a little bit of a different vertical exaggeration here to bring it down into a little bit of a slightly different perspective here. Let's go ahead and apply that. That'll flatten it slightly. That looks a little cleaner to me. And again, you're starting to see some of the structure of the terrain. I am just about out of time, but if I wanted to take this to the next level, I could generate some contours. Maybe that's my output product from this process. There's a contour generation function here as well for generating vector contours based on a surface model. So that was a very hasty walkthrough of the structure for motion process, and specifically within the pixels to points tool in Global Mapper. Hopefully you picked up a little bit of that workflow. Obviously, we didn't have a lot of time to dwell on the details. I like to remind folks where we started, though. We started with simple drone collected images, top-down overlapping views that we were able to process into this three-dimensional environment. Any questions? I believe I'm going to try to access the chat from off screen here, see if I can see the same as you. If you have any questions, feel free to use that chat window and type your questions in there as needed, and I will answer them verbally, or if necessary, I can answer them in writing as well. And again, I should have brought up on my screen, just give me a second. I also have an email address here. If you want to continue this conversation offline, if you've got any more detailed questions, feel free to use the email address that you're seeing on the screen. And if you want maybe a more detailed demonstration of this functionality or want to request a trial license of the software, by all means, go ahead and email the email address on the screen. Maybe reference where you heard this presentation, that you were at the conference, so we know who we're talking with. And we can set you up with a trial. So again, any questions, feel free to ask them in the chat window.